Very good afternoon, dear, and welcome back. Today we are going to discuss a very interesting topic: dexterity versus redundancy. Hmm? Now, before going into depth, just imagine this is my right hand. This is my right hand, and this is shoulder, this is elbow, and this is wrist. How about that if there would have been a joint here in between wrist and elbow, and suppose now my hand reach to wants to reach to my mouth, right? So right now what I am doing, I am, you see, I am reaching, means I am manipulating so many joints, this one, this one, this one. So it's not very energy efficient, isn't it? So uh, had it been a robot, the motor here, all has to be energized. But imagine the joint is here, and then my hand wants to reach to the mouth. So I will operate that joint and reach here. So if you could have more joints, then dexterity, this is called dexterity, dexterity would have been more. And manifestation of that you can see here in this image. You see, this is Dexter research robot, and since it is dexterous, I can wrap it around me and all kind of thing. And as I told that it can manipulate object with lesser energy. Why lesser energy? Because you will have to energize less number of joints. So dexterity is desirable, isn't it? So why not every robot has lots of dexterity? And to achieve dexterity, you need redundancy. That means you need more number of joints than required. Okay. So why don't you do all the robots with so many redundancy to extract dexterity? But why? Because it is costly. Costly in terms of control, in terms of hardware infrastructure, in terms of software development, everything is much more complex. And nevertheless, the Cobot and humanoid robot, they have redundancy to some extent. That's why I thought that it is great idea to introduce you how to actually tackle robots having redundancy. Before going to a Baxter type collaborative robot, here I have for you, I have three-link manipulators. You see, you have three-link robot manipulator. This is one, this is one, this is another link. And here is the point in the Cartesian space xy where a robot end effector, this is called end effector or gripper, needs to move. Okay. So this is my problem, right? Here I have, instead of two-link manipulator could reach that point, because here how many degrees of freedom in the Cartesian space you have? 2, x and y, because this point requires two independent coordinates for its specification. Okay. And to reach there, as you have seen earlier, the two-link robot was good enough, but I have deliberately kept xy. I am not attaching xy, phi, because on plane, as you know, instead of point, if it would have been a kind of 2D shape like this, then it required xy and phi. Phi is called orientation. And robot will require 3 degrees of freedom to actually capture or grasp this object. So I am not doing that. What I am doing, I am injecting redundancy, making my expression smaller, simpler, okay, because it is only three-linked robot. And you see, this is the concept, right? I have still xy, no phi, no orientation, and two-link robot was sufficient to reach, but I made deliberately one more link and one more joint. You see, this one, 1, 2, 3. and that essentially will cause redundancy, because more than required number of joints I have applied. So this is redundancy, meaning, and as you know, this will be having dexterity also, dexterous also, because if some point is here, only manipulating this joint, keeping all these two joints fixed, my end effector could reach here like this. Okay, I think you understand that. But here my intention is different. What I am trying to do, I have injected redundancy to a 3-link manipulator so that my expression will be still manageable. I can write here, and concept you will understand that how to solve inverse kinematics problem or inverse pose problem for redundant board. So as usual, I am writing x equals to L1 cos theta 1, L1 cos theta 1 plus L2 cos theta 1 plus theta 2, because just like earlier. And this is again L2 cos theta 1 plus theta 2 plus L3 cos theta 1 plus theta 2 plus theta 3. Okay, and let now write this because I will solve it using same Newton-Raphson algorithm. Okay, so now let us call it function 1, which is a function of theta 1, theta 2, theta 3. That is equals to this minus x equals to 0. This functional value has to be 0, and f2, this function, okay, taking this side and making it minus, taking it this side, making it minus, I am generating the functions whose roots I would like to figure out from numerical methods, right? So that's the same idea. So these are the two functions. Okay, this in vector form I have written. My function is f1, f2, and theta 1, and the theta vector will be theta 1, theta 2, and theta 3 is a mistake, so theta 3. Okay, so cleanly, in a clean way I should write equals to theta 1, theta 2, theta 3. Okay, you understand? So now I will have to run my Newton-Raphson algorithm. So this is the algorithm. For avoid complexity, you just call it 1. Okay, and you can, or you can keep it as it is. Okay. So now you see what is going to happen. Now let us see how to calculate the first derivative of these functions, right? So now I have multiple functions. Here it is 2, and multiple variables. Each function is of several variables, right? Each function is of several variables, theta 1, theta 2, theta 3. So this is, incidentally, I can write it, the function in general form. Function, the input space there is range is 3, and output is 2. So we are getting 2 outputs, f1, f2, and 3 inputs, theta 1, theta 2, theta 3. And essentially when there is a mismatch, okay, so this is your input and this is your m. When your m is less than n, m is less than n, then we call redundant. That means what you have, we are going to see. Okay. So first of all, first challenge is you need to figure out first derivative of the function, right? So 3 variables are there. So partial differentiation of function f1 with respect to theta 1, with respect to theta 2, with respect to theta 3. These are the 3 columns, right? First row, these are the 3 column elements. Second row, another function I have, and I am differentiating with respect to theta 1, theta 2, theta 3. Same what you have done. But now you see here, there is a problem, right? I have a non-square matrix, and the dimension of it is 2 cross 3. You have 2 rows and 3 columns. Oh my God, then how to invert it? Eh? So don't worry, we are taking the help of Wright Moore Penrose pseudo-inverse method, right? Using his method, you can just, those who know, fine, linear algebra we have studied. If not, then please brush up your, if you need to know more thing about it. But what it is, I am telling you here, okay? So first of all, the inversion. So inversion I need it, right? Here I need to invert it and then multiply it by this vector, right? Which is a how many functions are there? 2 cross 1. Huh? So, but I cannot invert the non-square matrix in a usual way. So I'll have to do pseudo inverse. Say this is my matrix, okay, and the pseudo inverse J pseudo, okay, is actually, this is Wright Moore Penrose pseudo inverse strategy. What we are following is that the first, this is 2 cross 3, right? You just transpose it. So the dimension of the matrix will be 3 cross 2. And then what is the dimension of the resultant matrix, which is inside the first bracket? You see, it is 2 cross 2. So as many functions will be there, its dimension will be that. In case of robot, it is here it is 2. So 2 cross 2 matrix. In case of this particular robot, it is 2 functions are there. Okay, so 2 cross 2. Then you can invert it, and then you multiply it by the transpose of the matrix 2 cross 3. So it will be 3 cross 2. So the pseudo inverse is actually matrix which is inverted. Original matrix 2 cross 3. You have just, original matrix 2 cross 3. You have just transposed, and on the right, okay, so that's why Wright Moore Penrose pseudo inverse. On the right, you are actually doing this juggling, that is multiplying the matrix which is transposed to make it forcibly square matrix. And by the way, this is quite general, as you will see. Say I have M cross N matrix, okay, which I need to invert. Okay, so what I will do in Wright Moore Penrose pseudo inverse method, what we will do, I will transpose this matrix. Okay, I will transpose, then it will be N cross N. In the right hand side I will transpose it, so it will be N cross M, and then I will multiply it with so this is my matrix M cross N, and then I multiply it with this transpose, which is N cross M, and then I make inversion of this. So it will be M cross M, and then this is the transpose of my original matrix, okay, M cross N. Transpose will be N cross M, okay, and inside matrix is M, always M cross M. So you have original matrix N cross M. Is it clear? So your here you see this is the same thing. So your original matrix 2 cross 3. So you do just like that, 2 cross 3 and transpose it, 3 cross 2 and invert it. Okay, and then original matrix transpose, multiply it by original matrix transpose, which is 3 cross 2, and that will be the pseudo inverse of this original matrix 2 cross 3, which is 3 cross 2. So I think this is what you will have to do, and there are functions for doing that. You understand, if you want to understand why it is so, theory you can read, but you will have to do it. And that's it. Now we are in a position to upgrade. That means to do this, which is equals to, say, theta n plus 1 minus theta n. So that is actually what is this? You need to so pseudo inverse then of the function f. So it's a function of configuration dependent, and then you multiply it by this function. Pseudo inverse you have calculated, multiplied by that function. So that will be the increment. Okay, until the increment is going towards some tolerance value, some nearing about some 0, that is 0.001, 0.002, you will have to continue the iterations, right? And believe me, you will reach to the destination. So, using Newton-Raphson method, this is just like similar to what you have already implemented, I believe, in 2x2 manipulator. So, earlier I have shown you the summation of one of my students' program. So you can extend it. Now you will have to extend. Not can, you will have to extend it. So initialization you will have to do, establish the function, okay, equation that equal to 0, whose roots will be theta 1, theta 2, theta 3, and make an initial guess, and then solve this Jacobian matrix inversion. You will have to do multiplied by function. So you calculate this, okay, numerically, of course. You solve, that is making tolerance value epsilon, right? So, and upgrade accordingly, and iterate until this less than epsilon, okay? You can choose, and terminate if the number of steps becomes too large, that is solution is diverging, the solution is diverging, and make fresh initial guess and repeat the steps. So that is the story I wanted to tell you about finding the inverse kinematics solution for a redundant robot. Okay.